Okay.
Okay. Okay, we have Dima Zakharov, who will be telling us all about Furstenberg and Kakeya problems for sticky sets of tubes. So, Dima, whenever you're ready, please do begin.
Yeah, thanks, Will, for inviting me to this interesting workshop. Um, okay, so I'll tell you something about Furstenberg and Kakeya. I don't plan to tell you that much about proofs. Um, and this is a joint work with Hongwang. Um, so I'll start with Kakeya. And for me, uh, um, Kakeya problem is the following statement. Let's say we have a collection of tubes in RD. So we have some parameter delta, which is like some really small number, and we look at tubes of length 1 and width delta. And the tubes have delta separated directions. And then kind of the statement of the conjecture is that the union of these tubes has almost maximum possible volume. So here's we look at the union of the tubes. And on the right-hand side, we basically have the sum of volumes of the tubes. So each tube has volume roughly delta to the d minus 1 because it has one long direction and d minus 1 short directions. And we multiply this by the total number of tubes. So we have a kind of bunch of tubes which point in different directions, then they can't really overlap that much. We allow this like small factor of loss here. So this is like a very concrete statement, which I kind of like. The way Kakeya is usually stated is kind of in the continuous setting where you have some family of line segments such that they point in different directions. And for every direction, you have at least one segment pointing there. And then you want to lower bound the Hausdorff dimension of the union of those segments. And this is like a discretized version of that statement. It's not completely equivalent, but it's very close in spirit. And if you can kind of answer this question, the chances are you can solve Kakeya as well. So, um, so recently there has been some very nice progress on this problem. So the three-dimensional case of this conjecture was solved by Hongwang and Zhao last year. And in fact, the statement they proved is a little bit stronger than this. And um, for what I'm going to discuss here, it will be kind of important to state the actual result. So the first kind of the first thing to state the result is that we will not study just the union of tubes. So like union of T, a bit what? Oh, it's interesting. But we will choose some subsets on these tubes. So for every tube in our collection, we'll choose some subset y of t, z of t, and we will consider the union of these sets y of t. So this is like what we call a shading. So you shade each tube by some subset, and you want to estimate the size of those. Um, um, this is kind of very natural thing to do. This allows you to like pigeonhole things and study the like maybe typical sets of points inside of the tube. Um, and this also allows you to get more precise information. Um, and this is also needed in applications. So um, if so, in the case of Kakeya, we usually think of these sets y of t of having density something like um, delta to the epsilon times the volume of the whole tube. So it's like fairly dense subset. Um, and if we want to get um, uh, the Hausdorff dimension statement from this discretized statement, you will need to consider shadings of like slowly decreasing densities. It's like a little bit smaller than 1 over log delta. Um, um, so shadings are useful. And another kind of more important uh, kind of strengthening of this conjecture is that the delta separated directions condition is replaced by something kind of weaker and more convenient to work with. So um, we consider sets of tubes which satisfy a certain convex Wolf axiom, which I'll define on the next slide. But basically, it's some kind of condition which says that tubes uh, in don't concentrate too much in some regions in space. And under those non-concentration condition, we want to prove that their union is still very large. Um, and um, so um, so let's say we have a set of tubes T, just as before. So we'll define the convex Wolf axiom of T. So we'll define the following constant, C convex Wolf of T. It will be the maximum over all convex sets U inside of RD of the number of tubes contained in this convex set divided by kind of the expected amount. So for a convex set U, we kind of want to expect at most like volume of U fraction of tubes to be inside. And so, what's going on? That's interesting. All right. It didn't happen before. What happened?
Yeah, you're welcome. Just try and restart it or something.
Yeah. Jeez.
That was a nice talk.
Yeah, well,
Even
it's a
quicker
short
than the
stock, I
previous
think.
one.
um, wow. Uh, I used the outdated version of the uh, Acrobat because it doesn't have these AI features which like are shoved into your face. So maybe it has some side effects. Um, okay, maybe let's not use the full screen because it seems to lead to disaster. Um, all right, so we were defining this convex Wolf axiom. You can see things, right? All right, so yeah, so we define this con convex Wolf constant as kind of the ratio of how much tubes concentrate in convex set compared to the expected amount. So this kind of ratio. And nice feature of this precise definition is that if T has delta separated directions, and it has kind of maximal possible size, then this means that this convex Wolf constant is upper bounded by roughly 1. If you have tubes pointing in different directions, then it's not difficult exercise to check that they cannot cluster in convex sets too much. Um, and so in what follows, we just want to kind of use this convex Wolf axiom instead of the directions. So and forget about delta separated directions whatsoever. And so this is what Hong and Josh proved. So they proved the following result. Let's say we have a set of tubes T in 3 dimensions, and this convex Wolf constant of T is at most some small power of delta, some delta to minus eta. And y, so for every T, we have a shading y of T with density delta to the eta, so also some small power of delta. Then the union of all these things, of all these shadings, is at least delta to the epsilon. And you pick your favorite epsilon first, and then you can choose corresponding eta. Okay, so this is kind of a very nice result. And so I'm going to talk about some kind of versions of this type of theorem, it's kind of more general things which kind of give more refined information. And all of these results will be of this kind of shape. So we will have a set of tubes which satisfies some kind of Wolf axiom. Maybe we will kind of put something slightly different here. And we will have some shading on those tubes. And maybe we'll put some different condition, maybe it will not be a dense subset, but maybe it will satisfy something else. And we will want to control the union of the shading. So this is kind of a class of problems, and that's what people kind of like to study. So let's see. So this is kind of what I just said. So we will have some set of tubes and shadings, and we will be interested in this set E, which is the union of those shadings. And so here is one conjecture, which is very well known, which is a maximal Kakeya conjecture. So it goes like this. Let's say we have a set of tubes in R3 such that convex Wolf constant of T is at most 1, or maybe like there's some small power here. And we have shading of density lambda. So maybe lambda is quite small. And then the conjecture is that the set E has to have volume at least lambda cubed. And this would be sharp. And the sharp example is simply taking E to be a ball of radius lambda, and your tubes are just kind of a hedgehog of tubes pointing in different directions, kind of intersecting this ball. And so the shading on each tube will be just this kind of segment of length lambda around the origin. And this is still open. On the other hand, in the plane, it's very easy to prove this conjecture, just application of Cauchy-Schwarz. But one feature of this conjecture is that this sharp example is very simple. So, so for every tube, the shading on this tube is just like an interval of length lambda, so it's like as clumped as possible. So it's interesting to ask, what if I know that this shading is not as clumped? What if like it's spread out a little bit better along the tube? Then perhaps the set E must be much larger. And so there are kind of several kind of ways to phrase this question. And in the plane, there was a recent very nice result by Hong and Shukun, which answers this question. So they call this 2n's Furstenberg estimate in the plane. So it goes like this. So let's say we have a set of tubes, and we know that they don't concentrate in convex sets, and we have a shading of density lambda on each tube. So that's so far is the same as maximal Kakeya. And we have one more restriction, is that the shading Y is 2n's. This roughly means that on each tube, the shading is not like concentrated on a short interval. So for any ball of radius delta to the epsilon 1, we have like the size of the shading inside this ball is much less than the size of the total shading. This much less you can think of this like 1/100. So like, every kind of smallish ball contains at most 1% of your shading, something like that. In reality, we need to put something slightly smaller here, some other small power of delta. But it doesn't really affect the bounds. So under this 2n's assumption, the volume bound on E can be improved quite a lot. So in the plane, the bound is lambda squared, so I didn't write it here, but like maximal Kakeya can be stated any dimension, and then it's just lambda to the dimension D. So it would be lambda squared if we didn't have this 2n's condition, and it can be improved to lambda to the 3/2 if we just assume like this mild non-concentration, which is quite surprising. And this 3/2 is sharp. So there's a sharp example where you can take the set E to be a grid, and tubes are just tubes with rational slope. So it kind of arithmetic example of this kind of sort. It's the same example as in the semi-Redit-Rotor theorem, if that phrase means anything to you. Okay. So this is a very nice result, and it has some nice applications. So this 2n's Furstenberg estimate can be used to make progress on the Fourier restriction. So Hong and Shikun managed to get a new exponent for the Fourier restriction estimate using this kind of incidence result. And they made a conjecture, which is a kind of three-dimensional version of this 2n's estimate, which kind of would also have implications for the restriction. So it's a kind of very similar statement. So here's what they asked. Let's say we have a set of tubes T in R3 such that the convex Wolf constant is at most 1. We have lambda dense shading, which is 2n's. And then they conjectured that E must have volume at least lambda squared. So comparing to the maximal Kakeya, this was lambda cubed, and just putting this very mild separation condition improves it to lambda squared. And they showed that this conjecture implies Fourier restriction um, by just combining it with refined decoupling. So, like, this is very nice. So there is like this very simple incidence geometry statement, which would have uh, major consequences in harmonic analysis. Um, uh, it turned out that this conjecture is a bit too good to be true. The counterexample can be found on Alex Cohen's webpage. But it still feels like something like this should be true. So um, this statement um, fails because this two ends condition is really maybe is too weak to uh, um, a bit of a too weak condition. But maybe if you can strengthen it a bit, maybe you can still save it. So it's still kind of very interesting question to think about. And uh, Hong and Shikun proposed a kind of approach to how to maybe study this conjecture by um, suggesting what would be a special case or what would be kind of an intermediate statement on the way to proving that conjecture. And that one is, we don't have counterexamples to, so that might still be true. And this is a kind of intermediate statement is what we call Furstenberg estimate. So let me now describe what this is. So Furstenberg estimate was originally proven in the plane, and that would be a three-dimensional extension of that. So here's the setup. So I need some fractal geometry terminology, which maybe on this workshop is not strictly necessary. So if I have a set of points P in some RD, then I say that P is a delta S set if intersection of P with every R ball is at most R to the S fraction of the size of P. So this is kind of basically the Frostman condition. Like if P was a measure, then this would be just a Frostman measure. But I like to think of discrete sets of points. And this holds between scales delta and 1. And usually I allow some delta to the epsilon loss in this bound, but I will kind of ignore that. And similarly, if I have a set of tubes, then I can also say that a set of tubes T is a delta T set if the same type of condition holds. So if the number of tubes contained in a thicker tube, so I pick any R between delta and 1, and I'll look at the tube TR, and I count how many tubes are contained in this TR, and I want this to be less than R to the T size of T. So this is a pretty natural notion. It kind of coincides with the Frostman condition for point sets if you view the set of all tubes as a kind of parameterized by some large dimensional space. You can describe a tube by a pair of vectors, direction and where the tube intersects kind of horizontal axis. Okay, so with these definitions, the Furstenberg estimate is the following result. So now let's say we have a set of tubes T, which will be a delta T set of tubes in the plane. So this is kind of what replaces the convex Wolf axiom. Now we put this fractal condition. the previous statement would be, you get the previous statement by taking t equals 1. And the shading y of t is a delta S set. So instead of just dense subset, we put some sort of fractal on each tube. In a setting of Kakeya, we think of S equals 1, essentially. So it's a generalization. And then in this case, we want to lower bound the union of these shadings. So you have t-dimensional set of tubes and s-dimensional shading on each tube. How large can the union be? And then there is some bound. It involves the size of each particular shading, and then there is some expression depending on the exponents, which shouldn't mean much to you. But anyway, this is a sharp bound, and it was a major result in the area like a couple of years ago. So, so what we want is a three-dimensional extension of this result. So one thing to mention before that, so this Furstenberg estimate was a kind of key ingredient in proving the two ends Furstenberg estimate, which I mentioned before. So this is kind of slightly more technical statement, but it's kind of you kind of have to use it to prove this nice two ends version. And kind of in a similar way to prove the three-dimensional statement, which is false, but okay. You would need a three-dimensional version of the Furstenberg set estimate. So let me describe it now. So we will need to modify the convex Wolf axiom for the tubes. So instead of convex Wolf axiom, we will have T convex Wolf axiom. So for a set of tubes T, we define this T convex Wolf axiom as the maximum over all convex sets U of the number of tubes contained in U divided by volume of U to the T, and then divided by the size of T. So just change how we weigh this volume factor, which is kind of a natural, pretty natural thing to do. And now the conjecture is the following. Let's say we have a set of tubes T again, for which this convex Wolf constant is at most 1. And suppose we have shading on the tube, which is a delta S set. Then the union of these shadings should satisfy some lower bound, which looks pretty similar to the two-dimensional statement, to the two-dimensional bound, but like the numbers are a bit different. Like the precise statement is not, the precise function here is not particularly important, but it just comes from some basic examples. The example, the middle term, again, comes from a kind of grid construction where you take the union to be the three-dimensional grid, and you take tubes to be tubes with rational slope. So, okay, now I can. So our work with Hong is kind of addressing this conjecture, but for now we only address a special case of this conjecture, which is kind of assuming that the set of tubes is sticky. So I will try to describe that next. So in the proofs of the Kakeya conjecture in R3 and the Furstenberg set estimate in the plane, in both arguments, the estimate was proven initially for a special class of tubes, which uh, depending on the area, people call almost irregular sets of tubes or sticky sets of tubes. Um, but those mean the same thing. Um, so it's a um, so it's a subclass of possible tubes, which kind of makes them easier to analyze. And then the task becomes to reduce the general problem to this special case. And this has been very successful in this kind of line of work. So what is a sticky set of tubes? So let's say we have a set of tubes T in RD, and we have some T, small t. Then we say that T is T8 irregular if the following holds. So I take some tube in T, so takes any tube in my collection, and look at the R neighborhood of this tube. So look at the tube, at the thicker tube of width R around my tube, and count how many tubes in T are contained in it. Then we say that it's almost irregular if this number is approximately this quantity, so the volume of the tube to the T times the size of the collection. Um, so if the set T is a delta T set, then the definition literally means that the upper bound here holds. So this collection of tubes is sticky if this upper bound is almost achieved. That's kind of where the terminology sticky comes from. Like tubes really like to be close to each other as much as possible. So, and this is the class which people kind of considered. So Arpon and Schmerkin proved the Furstenberg estimate for the sticky sets of tubes, and then Ren and Wang reduced the general case to sticky, and kind of both of those steps are kind of required. They like are completely different in some sense. So you can't really just prove the whole thing together. Like you need this intermediate step. And similarly for the Kakeya case, Hong and Josh initially proved the sticky version of Kakeya, following a strategy proposed by Katz and Tao in early 2000s. And then they figured out a way to reduce the general case, which was completely different argument. So like they sticky and non-sticky reduction have nothing to do with each other in some sense. And so in our kind of new result, we make this first step in this Furstenberg problem setup. So here's our result. So we consider the Furstenberg problem in R3, and we study the special case when the tubes are sticky. So let T be in T a irregular set of tubes whose convex Wolf constant is at most 1, and Y of T is a delta S set. So it's a shading which is S-dimensional. Then the volume of this tube satisfies the kind of conjectured lower bound. Okay. As a so this result is a generalization of sticky Kakeya estimate in R3 and of the sticky Furstenberg estimate in the plane, but the proof requires some modifications which do not appear in previous results. And actually, if we take our argument and specialize it back to the sticky Kakeya, the proof we get is actually different from the one used in the previous paper. So we get a new proof of the sticky Kakeya in R3. A lot of the steps are kind of the same, but there are some major differences. And we are this is a kind of work in progress. So we are kind of exploring how much else we can do with this new kind of approach. Um, but that maybe is for another talk. So let's see what else I wrote here. So there's there is one new kind of argument which appears in our proof, which didn't appear in previous works. I will not be able to describe it in that much detail here, but we call it kind of the diagonal tube argument. And basically, what it does, it kind of allows us to get kind of richer local structure of this Furstenberg or Kakeya set, kind of by kind of using tubes more efficiently in some sense. In If you know anything about the sticky Kakeya paper, there, roughly speaking, the argument reduces to analyzing horizontal grains and kind of vertical tubes. But we use like diagonal tubes as well. Anyway, so that's kind of very vague, and I'm not gonna go into too many details. But one kind of nice corollary of this approach is that when we do this, apply this to the Kakeya setting, then we don't need to analyze the C2 projection problem. So one part of the proof on the sticky Kakeya paper was reducing the problem to some C2 restricted projection problem. So like in R3, you have some set and you have a curve of directions on which you want to project your set. And if this curve has positive curvature, then it satisfies some nice exceptional set estimate. So we don't need that part anymore. And instead, we are doing something kind of very local, which kind of simplifies things. And for the sticky Furstenbergs, I think that's actually required. Um, like, okay, so let me very briefly go over the proof steps, and then I'll stop. I read on the instructions that my talk is supposed to end in 45 minutes, and I plan to stick to that. Um, so let me just kind of highlight what kind of case analysis appears in our proof. So we have our set of tubes and we have shadings, and we study this set E, which is the union of shadings. And for every point of our set E, we consider the set of tubes TP, which is just the tubes which pass through the point P in our collection. And if the set E is small, so if the shadings overlap a lot, this kind of by double counting means that the sets TP are very large. So we need to rule out the case when these sets TP are large. And then we analyze, we split into several cases depending on how these sets TP are kind of structured. So, namely, we look at how tubes in TP interact with planes. So we have three cases. So first case is when the tubes in TP intersects planes very poorly. So every plane contains very few tubes from TP. So it's kind of small concentration case. So then we use some high-low argument. So it's kind of some pre-analytic approach. Basically, locally we obtain some sort of restricted projection problem, and if the directions of tubes do not concentrate in planes, then that restriction projection problem satisfies some nice high-low estimate, which settles this case. High-low, if you don't know this kind of terminology, that means that you look at the Fourier transform of your set and you split it into high and low frequencies and analyze them separately. Okay, but this only works if there is this very strong non-concentration in planes. If tubes concentrate in planes a little bit, but not too much, then we reduce to ABC sum product. So I'm not gonna describe it in too much detail, but ABC sum product is some kind of statement which says that if you have some sets of numbers with lower bound on the dimension, then if you take their products and sums, then dimension grows very vaguely. So it's an additive combinatorial statement for fractal sets. And so in this intermediate case, our problem kind of splits into two instances of that ABC problem. Like in the two-dimensional sticky Furstenberg, Arpon and Shmerkin just reduce the general problem to the ABC sum product problem. And in our case, it's kind of has to split it into two because its dimension is one larger. And we need this intermediate case assumption to make sure that the two instances of the ABC problem kind of fit together nicely. Okay, and large concentration, so there's lots of tubes contained in planes. So this is like the most difficult case. So here, kind of proof is kind of parallels sticky Kakeya argument. So we obtain global grains and study the slope function. Yeah, that's like some words. And if you heard these words before, then the way we analyze it, we look at the slope function and consider two cases whether the slope function is smooth or not. And we use radial projection, ABC sum product, and this diagonal tube argument, which I kind of alluded to before, to analyze the set E. That's kind of a lot, but I just want to say that these are kind of the basic inputs. In particular, kind of radial projections play an important role, just as in the sticky Kakeya case. Yeah, okay. So I think I'll stop here. So I have two more slides with more details, but I didn't plan to cover them anyway. So I'll stop here.
Okay, let's thank Dima for a wonderful talk. I don't know if I can do that. I can just do it, not the normal one, I think. Are there any questions